Hey everyone, so today we're going to work on derivatives and integrals of exponential and log functions. We already know some of these, right? For example, we feel pretty good hopefully about this. Derivative of e to the x is e to the x times derivative of the exponent, or e to the u times u prime. And derivative of natural log of x is 1 over x times derivative of whatever's inside. So, 1 over u times u prime. Okay, so here's some new ones for you. As you know, e to the x is just a specific exponential. Like you could have other exponentials, 2 to the x, 3 to the x, things like that. So that's where we're going to use this new one here. Okay, so derivative of a is a real number. Okay, so something like I said, 5 to the x, 1/2 to the x, whatever it may be. You're going to do so similar to e to the x, and I'll show you how they connect. So 2 to the x times natural log of 2 times u prime, or a to the u times natural log of a, or natural log of the base times u prime. Okay, and does this connect for e to the x? It actually does. If you followed this new rule and you said, what's the derivative of e to the x? Derivative of e to the x would be, if we follow this, e to the x times natural log of e times the derivative of the exponent times 1. Natural log of e is 1, derivative of e to the x is e to the x times 1. So it actually still works. This is just a nice shortcut for only e to the x. Now if we have 2 to the x, 3 to the x, we have to remember this little tail ending here, which is different. Okay, and similar with log, natural log, as you guys might remember, is log base e. Okay, log base a, what if it was log base 5, log base 3, log base 10, whatever it might be. Here's your setup for that. So it'd be 1 over u, natural log of a, that would be the base. Again, a is a real number, times its derivative of the inside, or times u prime. Okay, and again, similar to e to the x, this actually does connect. Okay, and this connects by, if I were to do derivative of natural log is the same as log base e of u. You would get 1 over u, natural log of e, times derivative of u, or u prime. Okay, so natural log of e is 1, okay, and you would just end up, I guess I should have done x actually. Let me fix this a little bit. I kind of wanted to show with x. So natural log of x, 1 over x times natural log of e, times the derivative of x, which would be 1. And again, this just ends up with 1 over x. So this still works in that case as well. But please feel free, continue to use that shortcut, and just for any other logs, we'll have this new rule. Okay, so let's actually try some of these below. All right, so find dy dx, given y is this, x cubed, 5 to the 2x. So I hope you're thinking product rule, and chain rule might fall in here too. So we have x cubed, f prime would be 3x squared. Again, if you're comfortable without writing f and g, feel free to move on them. Here's the new part. Original function 5 to the 2x. G prime of an exponential would be itself times natural log of the base, so natural log of 5, times derivative of the exponent, so times 2. Okay, I would rewrite this like 2 times 5 to the 2x times natural log of 5. Okay, we cannot combine these. If you remember about exponentials, we can only multiply things with the same base to add the exponents. So 2 is kind of just like a coefficient and hangs out front. All right, so we're gonna do our little product rule here. So we've got 5 to the 2x times 3x squared. Again, don't combine that 5 and 3. Plus, let's see what we got over here. X cubed times 2 times 5 to the 2x times natural log of 5. And again, you can simplify that a little bit, but if it's free response, that is a perfectly fine answer. All right, let's take a look at one with log. Log of t cubed. We want to find v prime of t. Okay, so by the way, as a friendly reminder, if there's no base written, this is called the common log, if you remember from Algebra 2, and that means it's log base 10. So if there's not a base written, it's implying that it's 10. So we have log base 10, and 10 represents a. U is t cubed in this case. All right, so v prime of t is 1 over u, so 1 over t cubed, times natural log of the base, natural log of 10, times derivative of u, or times derivative of the inside. So times 3t squared. And if we move this around a little bit, again, you don't have to simplify this, but definitely worth noting you could. T squared and t cubed cancel to leave you 3 over t natural log of 10 as your final answer here. Okay, so there's another one with log. I want to show you 2 more here, okay, with e to the x and throwing in some chain rule in there. So take a look at dy dx. Y is equal to e, so let's rewrite this a little bit, e to the cosine of x cubed. Okay, so again, this is kind of your u, or that exponent, derivative of cosine of x cubed. If you guys want to write that first, since we're going to need it for chain rule, okay, would be the first thing you're cubing, the second thing you have cosine. So it would be 3 times cosine of x squared times derivative of cosine, negative sine of x. So I would just rewrite this as negative 3 cosine squared of x sine of x. Okay, and why do we need that? Well, when we take the derivative of e to the x, remember dy dx would just be e to the x, or e to the u, so itself, times derivative of the exponent, and now I already wrote that out, so I don't need to work any harder on that. Okay, just a little more complicated of a exponent. So that is that one. Take a second if you need. Again, what we're thinking here is derivative of the exponent, and this exponent was a little more complicated due to it being cosine cubed. Hopefully we're comfortable finding the derivative of cosine cubed at this point. All right, now we're going to look at dz dt. Okay, notice that we have some z's in here and we have t. So hopefully what you're thinking is I'm going to need implicit differentiation, which is kind of when we add those little taglines, dz dt, dx dt, dt dt, and making sure we take that into account. All right, so let's try this out. So derivative of 4z would be 4 dz dt. Again, we're taking the derivative in terms of t, so anything that's not a t, we need that little tagline. Equals, all right, derivative of e to the 1 minus z. Again, this is kind of your u, or e to the u. So e to the 1 minus z times derivative of that exponent. Okay, derivative of this exponent would be negative 1, right? So derivative of, and again, you're doing d dt of 1 minus z would be negative 1, that's the derivative of z, times dz dt. Okay, so that's where that's coming from. All right, plus 4 to the t. That's one of our new ones, right? Derivative of 4 to the t. Up there at the left-hand corner, a to the u, okay, would be 4 to the t times natural log of 4 times derivative of the exponent would just be 1, and so you don't really need that. And then derivative of the exponent also dt dt, but hopefully you notice that would just be 1. Again, we're taking the derivative with respect to t, so t is just act normal. All right, last but not least, e to the e. This is 2.718 to the 2.718. That's a constant, so it's actually just going to be plus 0. That drops out. E to the e is constant, so derivative of a constant is 0. If it was e to the variable, like e to the z or e to the t, that would be a different story. Okay? So now let's see what we have. 4 dz dt equals negative, I'm just going to move the negative in front here, minus z dz dt plus 4 to the t ln of 4. Okay. We're trying to solve for dz dt. So hopefully you remember this from last unit. We're moving everybody over that has a dz dt, excuse me. So I'm going to add over this guy. It's equal to 4 to the t, natural log of 4. We factor out a dz dt. Gosh, I'm like struggling to say it. And that's equal to 4 to the t, natural log of 4. Okay, I'll let you catch up there. Doing all this little algebraic manipulation here. We divide by that parentheses, and we end up with 4 to the t, natural log of 4, divided by 4 plus e to the 1 minus z. All right, so take a second if you need it. Same process we did last unit, which is get all the dz dt stuff to one side, okay, factor it out into the front, and then divide by that parentheses to get dz dt by itself. All right, last two examples we're going to do on derivatives. Take a look at 5 and 6. Hopefully you recognize these as definition of a derivative, right? Def of derivative, those limit definitions of a derivative. And we've got both a plus h, and then that limit as x approaches a. All right, so the first thing you want to look at here, by the way, this we should rewrite as 5 times 1 plus h, because we always want this to be in a plus h format. So right now it says 5 plus 5h, so we just want to rewrite that a little bit. So remember, what are we looking for? This whole thing represents x, right? So it'd be e to the 5x would be our f of x. We're looking for that. We are looking for f prime because we're taking the derivative, and we're specifically going to look at our a value, which in this case, a is equal to 1. All right, so derivative of an exponential, specifically e to the x, is itself times derivative of the exponent. Remember, if it's like 2 to the x, that has a slightly different derivative. It would have 2 to the x times natural log of 2 times derivative of the exponent. Natural log of e would cancel, so we get 5e to the 5x. And f prime of 1 would be e times 5 to the first times 5, which is just 5e to the fifth. All right, so that's our final answer there. Take a look at 6. 6 is that other definition, f of x minus f of a over x minus a as x approaches a. So we can kind of line this one up. This one always is a little bit preferred because it's a little bit easier to see what's going on there. So let's take a look first at what f of x is. So f of x is natural log of x squared, okay, and a is e to the fifth. So again, we want to find f prime of a, so f prime of x. How do we find the derivative of natural log? That's 1 over the inside times derivative of the inside. That just gives me 2x over x squared, which is 2 over x. All right, so our last step here would be f prime of, not 5, sorry, e to the fifth, which is 2 over e to the fifth instead of 2 over x, and that's kind of it. All right, so to finish up these notes, guys, we're just going to talk about integrals of exponential and logs. So similar to the beginning, we know some of these, right? So some of them that we know, e to the u, antiderivative of e to the u is e to the u plus c. And we don't forget anti-chain rule, right? Times 1 over u prime. So those 1 over u is natural log of absolute value of u, and e to the u. Hopefully you guys recognize those. Okay, here's some new ones that we want to recognize, and these are always a little bit tough. If you have a setup like this, you want to recognize it's that exponential situation, okay? If you have a setup 1 over x, natural log of a real value, a real number, you want to recognize that that might be a log function. Okay, so we're going to try these first 4 here and save the last one for class. So take a look with me here. Okay, again, we're kind of still considering anti-chain rule. We will move on to doing u sub. So if you've heard of this word u sub, I promise you we're going to do it. For now, I think it's good to recognize and actually make our lives, I think, a little bit quicker by doing anti-chain rule. So first thing we're looking at is kind of that overall function. We've got e to the 4x squared. This is kind of your little inside chain rule that you're going to have to do anti-chain rule for. Okay, and here's some result of the chain rule that's already sitting there. Okay, so again, when we rewrite this, we do result just hangs out. Antiderivative of e to the x would be e to the x, or e to the u, whatever you want to say. Okay, times anti-chain rule. This was the piece we're worried about for chain rule, so we're going to do 1 over 8x plus c. All right, so 8x and 4x slightly cancel to be 1/2. So 1/2 e to the 4x squared plus c. Okay, and I always encourage you, if you're not sure if this works, please take the derivative of this and see what you get. Take the derivative, you'd bring down an 8x, it would cancel to be 4x, you still get e to the 4x squared, etc. If my audio doesn't make sense for that, try it out by yourself, by hand, pause the video and take the derivative. Should match this original. Okay, so take a look at number 2, 5 to the x, natural log of 5. That should look a lot like something we know right here, guys. It's matched up exactly, so we notice that its antiderivative is just 5 to the x. Okay, this whole thing is a result of, if I took the derivative of 5 to the x, right? Derivative of 5 to the x is 5 to the x, natural log of 5, times derivative of x, or derivative of the exponent. So since this matches, my original function was just 5 to the x plus some constant, right? And that's my final answer, because if I take the derivative of that, here's what I would have gotten. Again, you want to think in that cycle. How does this connect? Antiderivative and derivative. Okay, so next one we have kind of a tough one, I think. Number 3 is one of the tougher ones here. So we see an x squared. That's going to be result of chain rule here with this little guy. Okay, 9 to the u. But then we would have had, if you look at the last problem, we had something with natural log. So we would have had that same situation here. So the issue with this one, and again, it's a little bit hard to recognize, is it's missing, okay, a natural log of 9. That should have been in the result, okay, if we're comparing it to here. Should have been right there. So we're going to have to take that into account and make sure we divide by natural log of 9 instead. So let's take a look here. We're going to leave that result of chain rule. Okay, we're going to multiply by the antiderivative, which would be 9 to the x cubed, or itself, okay, times 1 over chain rule, 3x squared. Last thing, again, a little weird, we didn't have a natural log of 9, so we need to divide by natural log of 9 to take that into account, plus c. Okay, x squareds cancel out, and 3 ln of 9 is in the denominator, so I could rewrite this as 9x cubed over 3 natural log of 9 plus c. Okay, and if you're a little bit confused about how this works out, if you were to take the derivative of this, okay, this is the final answer. The derivative would be 9 to the x cubed, and 1 over 3 ln 9 would have been hanging out here. Okay, times natural log of 9 times 3x squared, right? That's the derivative of an exponential. So natural log of 9 would cancel out, 3's would cancel out, and look what we have left. 9 to the x cubed times x squared, which is the original. So that's why we need that natural log of 9 in the denominator, since it wasn't in our result of chain rule. Okay, so that's what we're going to try here. 1 over x, natural log of 4. That, again, what I'm looking for is that it's hopefully familiar. Okay, right there, 1 over u, ln of a. That is exactly matching up with log base a of u. So let's take a look here. Okay, if we compare this, that would be like u is equal to x, right? Matching up here, that means the inside is x, and a is 4. So this is the exact result of, if I took the derivative of log base 4 of x, I would get 1 over x, natural log of 4, times derivative of the inside, which is 1. All right, so final answer here would be log base 4 of x plus c, since it is the exact derivative. All right, so thanks again for watching. Take a second and rewind if you need to. I hope you feel comfortable at 1, 2, and 4. I think 3 is kind of a challenge, but hopefully you're understanding where that natural log of 9 divisor came from. And number 5 we'll work on in class. That's a good challenge as well. And again, if you're making that study guide, definitely good things to put in your study guide right here, right? Definitely important info. And that first box with derivatives. All right, so thanks again for watching, and please let me know if you have any questions.